In this video, we're going to be learning all about critical numbers. A critical number, also known as a critical value, is the x value c of a function where the derivative is equal to 0 or the derivative does not exist. If we're referring to a critical point, that's going to be the x and y coordinate, which would look like c f of c. Let's talk about how this relates to extrema. So relative and local extrema occur at critical values or critical numbers. Absolute or global extrema can occur at critical values as well, but they can also occur at endpoints. Just to note that other textbooks and curriculums might define things differently here. This is the definition we'll be using in all of my videos. All right, let's examine a graph. That's one that we're pretty comfortable with, which is just a parabola. This is something we see a lot in Algebra 1, and we talk about in Algebra 1 how to find the vertex, for instance, or the turning point of a parabola. Well, that vertex and turning point is the same idea as an extrema. We're just changing the terminology a little bit. So if I were asked here, identify any extrema and where they occur, I can definitely see that I have an absolute minimum of -4 that occurs at x equals -3. Now it says use the definition of a critical number to verify our answer. Well, if we know critical numbers are where the derivative is equal to 0 or the derivative doesn't exist, let's start by finding the derivative of the function. Using power rule, I would get 2x plus 6. If I set the derivative equal to 0 and I solve this, you can see that I'm going to get x equals -3, which matches the critical number that we found where the x, which is essentially the x coordinate where the absolute minimum occurs. So if we think back to Algebra 1, you learned this formula x equals -b over 2a. So this formula was used to find the equation of the axis of symmetry of a parabola, or you used it perhaps to find the x coordinate of a parabola's vertex. So in Algebra 1, you likely just were taught and given that formula and you memorized it, but really it stems from calculus and the idea of critical numbers. This is because a vertex is an extrema. So let's look at where it comes from. If we look at standard form of a parabola, f of x equals ax squared plus bx plus c, and we take the derivative of it, we would get f prime of x equals 2ax plus b. If we solve that for x, we move the b over, we divide by the -2a. There comes our formula for axis of symmetry, or again, the x coordinate of the vertex, which is x equals -b over 2a. So again, that's formula that you learned in Algebra 1 really stems from this idea from calculus. All right, let's look at some problems where we are going to be finding the critical numbers. So we're going to look at a whole bunch of different functions here. So let's start with number 1. We have a cubic function. So to find the critical numbers, we're going to start by taking the derivative using power rule. And then we are going to solve by setting it equal to 0. Now for a cubic function, the function always exists, or the derivative always exists as well. So we don't have to consider that scenario here. When we get to number 2, we'll talk about that other option. So for right now, we're just going to set the derivative equal to 0. All right, to solve this is not immediately factorable. We can do factor by grouping though. So I'm going to do 3 times 4, that a times c gives me 12. And then I'm going to think of two numbers that add up to -8 and multiply to 12. And I'm going to rewrite this in 4 terms. So 3x squared minus 6x minus 2x plus 4. So we're really just rewriting that -8x so that it works better for us in terms of factoring and solving. So now I'm going to factor by grouping, pull out the GCF here of 3x. Pull out the GCF here of -2. And we'll group to get 3x minus 2 and x minus 2. Set each factor equal to 0. And we get x equals 2/3 and x equals 2. So those are our 2 critical numbers. Okay, number 2. g of x equals x plus 5 over x squared. Okay. We might also think about it this way as x plus 5 times x to the negative 2 power. And that makes it a little bit easier to take the derivative. So if I take the derivative here, derivative of x is 1. Derivative of 5x to the negative 2, bring the negative 2 down, subtract 1 from the exponent, and I have negative 10x to the negative third. And I'm going to also just rewrite this here. A suggestion when finding critical numbers and you have two terms like this where one is a fraction and one is not, is let's get them both to be fractions by using common denominators. So I can multiply here by x cubed, top and bottom, so that I have a new expression here. I have x cubed over x cubed minus 10 over x cubed. And now that we have common denominators, we can actually combine the terms in the numerator. So when you have a fraction for the derivative, remember that didn't occur in number 1, but when I have a fraction for the derivative, we're going to consider two scenarios. So one is where the derivative is equal to 0, and the other is going to be where the derivative is undefined or does not exist. The derivative will equal 0 whenever the numerator equals 0 here. So I'm going to solve this by setting x cubed minus 10 equal to 0. X cubed equals 10. And then x is equal to the cube root of 10. To determine where g prime of x is undefined, well, a fraction we consider to be undefined when the denominator is 0. So now I'm going to set denominator equal to 0. And that will just give me x equals 0. So these are my two critical numbers. So to recap that, the derivative equals 0 when the numerator is 0. The derivative is undefined when the denominator is equal to 0. All right, moving on to number 3. M of x equals x times e to the x. So when I take the derivative of this, this is going to be product rule because I have two functions being multiplied by one another. So a derivative of the first term times the second plus the first term times the derivative of the second. And recall that the derivative of e to the x is just itself. Let's clean this up a little bit. And we might notice here that we can set this equal to 0 as well, but that we have a greatest common factor of e to the x that we can essentially pull out. And now let's set each of these factors equal to 0. E to the x equals 0. It is not possible to solve that. However, 1 plus x equals 0, that we can solve, and we would get that x is equal to negative 1. So that is our only critical number here. All right, number 4. F of x equals 1 over x squared minus 1. All right, so we have a fraction here, so we're going to use quotient rule. So derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. All right, this can absolutely be cleaned up a little bit. Over here, everything is going to go away because we're multiplying by 0. So I have negative 2x over x squared minus 1 squared. This is a similar scenario now to the problem above it, to number 2, where we have the derivative as a fraction. So we're going to consider the two scenarios where f prime of x, is equal to 0, and when f prime of x is undefined. So where the derivative is equal to 0, we set the numerator equal to 0. Where the derivative is undefined, we set the denominator equal to 0, and we're going to solve each one of those. Over here, I will be getting x equals 0. Over here, I'm going to get x is equal to plus or minus 1, and those are my critical numbers. So x equals 0, x equals 1, and x equals negative 1. All right, for our last question, it says identify all extrema of the function f of x equals sine of x plus cosine x on the closed interval 0 to 2 pi. And it says hint, recall where absolute extrema may occur. So just a note here on this one, we are asked for the extrema, not just critical numbers, but we're asked for the actual extrema. So let's start the same way. We're going to take the derivative. Derivative of sine x is cosine x. Derivative of cosine is negative sine. And we're going to set that equal to 0. Now this looks initially maybe a little difficult to solve, but if we recall some old knowledge about trigonometry, we could solve here. So I'm going to move the sine x to the other side. So we're looking for where sine of x is equal to cosine x. The first thing I'm led to do is think about all students take calculus. If sine and cosine are equal, their sines must be equal. So that could either happen in quadrant 1 or quadrant 3. So note, it cannot happen in quadrant 2 because sine is positive there, cosine is not. So again, we should have two answers, one that's in quadrant 1, one that's in quadrant 3. Now, if we also know our special right triangles, you may have initially learned them as 45, 45, 90, but we can also think about them as pi over 4, and pi over 2. That's really what we have here for that right angle. And here's what the sides would look like. I can see here that the sine of pi over 4, think about SOHCAHTOA, would be 1 over radical 2. Cosine of pi over 4 would also be 1 over radical 2. So I can tell that from looking at my special right triangle, the first value of x where this would be true is pi over 4. Again, if it helps you to think about it in degrees, even though our answers will be in radians, because look at our interval, it's in radians. But if it helps you to think about it in degrees and work that way, that's perfectly fine to do. In fact, when I go back to this all students take calculus, 45 degrees is in the middle of quadrant 1, right? So I know that I've basically found my answer from quadrant 1. Now I need to find my answer from quadrant 3. So if you recall, when you are doing, I'll write in degrees here for a moment. When you're working on a graph, quadrant 1 goes from 0 to 90. Quadrant 2 goes from 90 to 180. 3 goes 180 to 270. And then 4 goes from 270 to 360. And those are coterminals, 0 and 360. So over here in quadrant 3, this means our reference angle is 45. So that total angle would be 225 degrees. So if you watch as I start at 0, going all the way here would be 225 degrees. So now let's find that equivalent in radians, and that would be 5 pi over 4. So those are our two critical numbers, pi over 4, 5 pi over 4. So I'm just going to make a little note that those are our critical numbers. Now, let's go back to the hint from before. It says, recall where absolute extrema may occur. So absolute extrema can occur at a critical number, but it can also occur at an endpoint. So even though there are only two critical numbers, there are 4 values that I really need to consider. So an extrema can occur at 0. It can occur at pi over 4. It can occur at 5 pi over 4, and it could also occur at 2 pi. So just a note here, these are our endpoints, and these are our critical values. Okay, and in the next lesson, there will be more practice too with the absolute extrema. So to find the y values, I'm going to plug 0 into the original function. So I would be doing sine of 0 plus cosine of 0. That would give me 1. When I'm finding sine pi over 4 and cosine pi over 4, remember how the sine was 1 over radical 2? Cosine was 1 over radical 2. We could also, if you know how to rationalize them, you might have learned that those are radical 2 over 2 plus radical 2 over 2. So that gives me 2 radical 2 over 2, or just radical 2. Now we've already established that this is going to be the same answer over here for 5 pi over 4. And 2 pi is going to be 1 again, because 0 and 2 pi are the same thing. They're coterminal angles, so the answers will come out identical there. Okay. All right, so if we're looking for the absolute extrema, that's going to be the highest value. That's going to be, look at our y values. We have 2 values of 1 and 2 values of radical 2. Okay, the square root of 2 is something higher than 1, right? Even if you don't know exactly what it is, if you think about it this way, radical 2 is somewhere in here, right? So we know radical 1 gives us 1. We know radical 4, or square root of 4, gives us 2. So this has to be something between 1 and 2, so definitely greater than 1. So these are going to be our absolute extrema. So there's an absolute extrema of radical 2 that occurs at pi over 4 as well as 5 pi over 4. Since endpoints cannot be relative extrema, the points at 0 and 2 pi do not produce any extrema here.